Section 2, which is titled Punch for All. The first speaker is Sherilyn Moreau, who's our outreach lead on Punch, and she's going to give us an update on all the outreach activities that she's been working on. Take it away.
Thank you, Mahir, and thanks for coming in from the break. For appreciating you. That's what this presentation is about. Appreciating our science community for helping us make this outreach program as successful as it can be. And we are a multi-institutional program, and we're really grateful to be included in the launch celebration. Hi, Jack. I have to say there's another mentorship for me there in heliophysics, not heliophysics, helioseismology. Dare the word be uttered. Good. All right, we are really excited to be here for launch. These are some of the outreach team on the ground here, and I encourage you to be interacting with them. There are also many others tuned in from afar to this exciting milestone and helping us shine in the light of launch along with you and benefit the community here as a result of the launch being here. So we really appreciate ongoing support from our leadership, our PI, of course, Craig DeForest, and Sarah Gibson, our project scientist, and Nikki Weil, our mission scientist, have been really close support for our integrated outreach effort, and we're very, they've been there all along, right, from the pre-proposal stage. We're also grateful for a number of you new people who have stepped up over these last years and participated in really powerful ways that I hope to illuminate in this presentation. And those of you who still, we haven't got the data down yet. There's a lot of discovery, there's a lot of cool stuff yet to come. And so your engagement remains very important to us. I'm on a show of hands, how many of you have been asked in the last few years to give a public talk related to punch science? Not enough of you, maybe. Okay, we want to support that. We want to support you in outreach. And I want to, John, if you could show up the stickers and the projectors. Don't see, if we could hold up some projectors. I would love, we got a lot of stuff out there and we don't want to ship it back. Okay, so can you keep those up for a moment, please? Thanks. So brand new stickers. The outreach thing, kids love these. We know that kids love these. Let's see, there we go. Okay, the slide isn't advancing. Okay, I have to do.
You can use theirs.
All right, thank you. Yeah, so like these kids down the road here toward Vandenberg, right? 500 in an assembly, 500 students just a couple of days ago. We gave 30 of the projectors. Could we hold up the 3-hole punch pinhole projector for those who are unfamiliar? We want each of you to take 30 of them to give a teacher, right? You are our agents. You are involved in the punch mission, and it's powerful for you to speak. And so if you're not the kind of person who does public talks, it's okay. Go to your kid's school, go to your grandchild's school, and give a teacher a classroom set of them. They will love you forever. And a sticker for each kid who participates, right? So take a wad, right? Take 30 of them, take 30 projectors. I didn't want to get rushed to say that at the end, all right? So we really have a lot of stuff here for you and for kids like this elementary school. I gave every teacher a pack, and I'm suggesting that you do that too. Here we had a public outreach event on Sunday leading to launch, and these are a couple of really important people who are dancing up a solar storm. And at the end of the table, we have Alexandra Lockhart, and you see her down in the middle. She was leading a crowd of people. If I could have a wave of some scars, maybe Sarah will have an opportunity to put that dancing up a solar storm on the break, and you too can interact and make like a solar storm. It's a 15-minute video guided art science activity that was quite a hit on Sunday. And so we're grateful to professional dancer and choreographer Alexandra for that time in the sun. And so these folks will be a part. If I manage to get through this, you can interact with them at the end. All right. So this is all exciting and fun and collegial to be embedded in your mission, our mission. We own it. That's why so many of us are here. But it's just as important that the strength of the relationship that's been built over these last years results in far better products, right? We have more accurate products. We have more relevant products. We have, it's led to higher quality products and events that would be possible without such a collaboration and rapport. So we've now matured to a really high functioning level, and we're poised to leverage this foundation with other partnerships, including PBS, an art museum in Santa Fe, a national professional development program for teachers. There's so much opportunity for us as we move forward into STEM, as we move forward into Phase E. How many of you have used or seen, you've used our pinhole projector? Okay, great, great. And they're not just for eclipses. They performed beautifully for the eclipses, as you can see in these images. That left one is the daughter of our evaluator, Dr. Sandlin Buxner, Anis, and she teamed up in the plaza of Pueblo Bonito in Chaco Canyon to create that annularity image. How about that, right? It's a beautiful image. And the other image there comes from the Kentucky Science Center. We have people who will be happy to show you how this works. We have a 6-minute video that will teach you all the results of our field testing about how to get the biggest ahas and gee whiz moments out of a 3-hole punch pinhole projector, not just a 1-hole. It's a game changer, and probably nobody else is going to do it again. Do it a different way again. You may put other shaped holes. I want to acknowledge, actually, at this moment, Rebecca Robinson, and can you stand up, please? And Simon Steele. These two are from the Muse project, right? They are the Muse outreach leaders, and they have adopted our projector with their branding, and you'll see that on our poster outside. Yep. Also, the Shield Drive Center, where Sandlin was the first adopter of the 3-hole punch pinhole projector. So they take our products and our leads and links, but put their own branding on it. As Craig likes to say, this product has legs, right? And unabashedly, I will say, of all the pictures that came in from around the country, over 350,000 projectors were distributed in combination with our dissemination partners. Educators in every single state of the country received these, and the joy and delight in the photographs we received back was crazy. If you facilitate this well, you see the faces, right? Both indoors and outdoors. You can really delight people. And I remember being shoulder to shoulder with Sarah at an AGU meeting, running this activity on the tables and delighting scientists like yourselves, as well as kids and non-scientists. I have a little poem: on a beach, in the street, on a tarp, in the park. What do you think? All over the place. Also, exciting curiosity, 4-year-olds to physicists. Here is Nikki Weil with Al Roker. And so the legs extend. We are connecting NASA high-tech to nature, giving people an opportunity to look at the pinhole images of the sun. They're out here on the concrete and making the connection to the foundation of what it means to make an image with punch cameras or with the pupils of our own eyes. You all recognize those as images of the sun, right? The outreachers are nodding. Yes, those circles of light. Nikki Weil on the Today Show. And in our recent outreach event right in this room, she gave a talk, public science talk, as well as Craig on the Cal Poly campus right here in this room on Sunday. We have these birthday sunrises banners. They're not out there this time, but I really thank Nikki for encouraging all of you to make observations of the sun and see how the sunrise position changes with the course of the year, which is, of course, what our ancestors did. So Jim and Dave are holding up. Jim is the space science director at the New Mexico Museum of Natural History and Science, and a very key Punch outreach partner. I didn't mention the fellow who held up the logos, but that's the Fisk Planetarium Director from the University of Colorado, Dr. John Keller. Yeah. We also have Dave Dooling in the blue shirt, and he is made a nifty little polarization wheel that you will see out on the table. Yes. Yeah, so we have an incredible team, just like the science and engineering, right? So we're experimenting with numbers. This works very well in virtual workshops and conferences where people can put in the chat their birth date and a number, a horizon number for where the sunrise would arise. Now that's to the 15, 5 minutes to the 15. To the 15 or? Excellent. Here's Ronnie Killo, whom you saw again early this morning. Notice that the ceiling lights can be imaged. He's at the Adler Planetarium during an outreach event at AGU. The indoor demonstration is set up outside. I encourage you to play with it at least once over the next 2 days. Here's celebrating Gilly Gilbert, who helped us with seeing with your hands. We have these tactile objects out there. These have been developed with and for blind learners, but are valuable for everyone. We collaborate with these folks to make activities valuable for everyone. You too can see with your hands outside. It's quite fun to do this synesthetic activity. If you could also hold up our other prop, we have a full-size model of this famous now Chaco petroglyph. Nikki Vile will be using this, we hope, in the launch broadcast that will be happening. It's hand-sized. Hand-sized. That's the real size of the petroglyph in Chaco Canyon. How many have been to Chaco Canyon? Not enough of you. Just say, not yet. And this is right off the visitor center parking lot. And Gilly was helping us at an AGU poster. This fellow came and talked to you after at the NCAR booth because he was interested in research opportunities. So these things have a way of rippling into goodness. I'm gonna flash through these. We're gonna do the best job of polarized light education that's ever been done. Why shouldn't it be punched? And we are developing scavenger hunts. Polarized light is all around us. How many already knew that polarized light was polarized? That rainbows were polarized along the direction of the arc. Try it out with your punch polarized glasses. Yes, I will. Monarchs use it to navigate, and kingfisher birds use it to dive in the water and get fish, right? So it's a really neat NASA nature connection. That's one of Craig's boys. And so Craig, among the many other things he does for our outreach program, he takes pictures of his son with the glasses, right? And helps advise us on our science. Try it out on any screen. If you have polarized sunglasses, try any of your screens, handheld, any screen that's around here, and detect the polarized light. It's in our everyday environments. This is one of the activities that we do, testing a screen for the presence of polarized light. In this case, the screen is polarized horizontally, but many of them are also polarized vertically, and it's delightful, right? It's just delightful. So there's a cool animation. Isn't that neat? Oh yeah, we're going a long way with that. We're going to have a kinesthetic activity related to this and a very disciplined way of waving your hands. There's some space hardware that we expose to the learners to connect with the rotation of polarized glasses. And Dave, if you could wave your filter wheel again, we're going to try to add that in phase E, this idea of a handheld filter wheel instead of rotating the glasses, which can be confused with solar protection glasses. There's my rainbow slide. So fun to play with rainbows. Parker, we're doing a Parker Punch Palooza at Fisk Planetarium, and we just did a Punch Parker Palooza at the New Mexico Museum of Natural History and Science. That went very well. Dr. Chris Lauder was the featured presenter, and I think you all know who he is, and if you don't, you'll hear him for 40 minutes in a second. And we're really, do you have I didn't cue you. Hang on, it's coming. All right. I want to call out Elena Provornikova. Did I say it anywhere close? Okay, she has been instrumental in providing visualizations for our Dancing Up a Solar Storm with Alexandra Lockhart, and also in working with John Keller and his team at Fisk Planetarium for the short planetarium on Punch. So there'll be a full dome film, a short dome film, and a flat film released in early April related to PUNCH. And there, in particular, there's a gamma pipeline, and maybe in our 5-minute Q&A, John can say a little more about that. And there is Chris Lauder. Chris, can you just come up and say a sentence related to your experience, your recent experience at the Punch Parker Palooza in New Mexico?
Yeah, it was a great experience, great museum. I would say that the materials that you provided helped keep kids' attentions, even though there was an animatronic dinosaur.
We beat out the Amazon Prime store. See that this work is good for the world. Thank you. All right, so we want to fill out this part of our outreach element of our website. And we want to hear from you about what supports you as the data is coming down and science is being created. We want to be at your side. What is it that helps you be a member of this outreach team? Not just public presentation, providing of data, checking for science accuracy. There are all kinds of roles. There's a whole spectrum of roles for supporting the outreach team as we move into Phase E. So Sandlin, Dr. Sandlin Buxner here, who loves to work with the team cards. By the way, I want to acknowledge everyone who is featured in the team cards. And in Phase E, we hope to, yes, thank you, Robin. I saw that thumbs up, right? We want to ask more of you to participate, but we need to move on into the next phase of the mission. Thank you, Sandlin. She also will be coming around informally asking you some questions about what supports you best in regards to participating in our outreach effort, okay? And so it's not at all too late. So there is the QR code, find it out on the table for our outreach activities. We have more to do in collaboration with other missions like Parker and Muse and IMAP. The outreach leads are in communication related to that. All right, thank you so much.
Anybody has a question, please come to the microphone in the middle of the room.
Sure, another question, but many of us know what a great singer you are. Should Punch have a theme song?
We have a lot of art and science stuff, and I haven't yet had the time to put my Astro Jazz. I think you probably heard, you probably heard a Storm's song from me way back when, Jack, and I haven't had time to put that on it, but there is something Sarah produced related to iCorona, right? We don't have that on our website yet, and I don't know if we're allowed to, but we can point to it. Yeah. So thanks for that. Yeah.
Less of a question, more of a comment. All of these outreach products that Sherilyn has showed all of us are vetted. They're all tested. They're rigorously designed and iterated, and they work. I'll relate briefly. Those team cards in particular are not a vanity project. Those are able to help kids ideate on, I might be a scientist, and they really work. I'm amazed. Every single one of these products is it's wonderful to see it happen.
Thank you, Craig. You know, and you're an inspiration for that. You put up a chart earlier in your presentation that said, we're on the leading edge of this and this and this. We are too. In our world in science education, we strive for that very same thing, to be on the leading edge of astronomy education and to be inspirational to our colleagues around the country in planetariums and science centers. So we are having that kind of impact, and to have to Rebecca and Simon here and other representatives is just thrilling. Just as you and Sarah broaden the science community beyond the COIs, we want to do that in Phase E and broaden our community of outreachers, and we're ready. We're ready to launch like you are, and we're ready to make that difference in the nation.
Curious if copies of that life-size Chaco sun glyph are available for outreach events, because that's an awesome thing.
John? Good.
They can. We actually, I do not have it here, but it is out on the table. We have a small 8x8, which is a much more standard STL file format for people to 3D print their own versions across the world. These were made by Boulder students using a cast resin process, but this STL file can be made available. It's just that many folks don't have this large of a format of a printer to do the STL file.
And Steve Cranmer, you know, we got other stuff to do in Phase E, like the life story of the solar winds and what's happening in the heliosphere in collaboration with our sister and brother heliophysics missions. I want to acknowledge, I just see Sam over there. Sam stepped up and said, I want to be involved in the outreach here. And we didn't do very well by that, but we decided we we're going to do, thanks to Sarah, an Ask a Scientist booth when we're here like that together. That's such an obvious idea, to just have a table with some nice things that people can come up and interact with somebody who's on the front lines of doing punch science. And so I want to acknowledge, Sam, you're stepping up this time. Thank you.
Any more questions for Charlene? No?
John, could you do, if I have 1 minute, do I? John, if you could say a little something about the Gamera collaboration and Elena, wave your hand. Oh, you're a great hero for us with the visualizations.
Briefly, been working with Slava Merkin from the CTS Drive Center, as well as the EASY mission. We were able to put together a nice visualization for full dome using Houdini, taking Gamera pipeline data, Gamera data into a pipeline of Houdini to make a nice visualization for EASY. We're using that same pipeline for the full dome film we're making for Punch. And with actual data, so this is all simulated data, but with actual data, I think there's a lot of great opportunities to have full dome visualizations of your research data. I have it on my laptop and share with you the current version of what we have, and I'd be happy to work with you over the next 2 years and have filmified versions of full-on Punch data sets.
Stanley, could you just say something about what you intend to do here in the next couple of days?
Yes, I'll just be chatting with those of you who have done outreach to just kind of understand how you can be better supported, and then folks who might be interested, understand how we can better get things to you and support you.
All right.
Okay, one more last question. Go ahead.
Uh-huh.
I should make a comment. You know, much like in the world of science, Punch has kind of demonstrated something which is tied together our missions. Something that, you know, often when we do mission, of course, each mission has its own focus science goals. And Punch has actually punched through that and integrated a whole host of other missions. And they're not just solar physics missions, they're interplanetary missions. IMAP will be launching, they're geospace missions, easy as Therese was saying, there'll be 6 missions launching, but a whole host that already exists. So in that same spirit, you know, I think the outreach team deserves a lot of credit in the way you have developed products and have gone to these various teams and socialize the ideas of doing an integrated outreach. Thank you much.
Thank you for seeing that, Mika. All right.
Great. Okay, so the next talk is an invited talk, just like the previous one. Marcus Hughes is going to tell us all about the Punch Science Operations Center. The next 2 talks are going to be a little bit different from what you used to, because there might be more interactive on workshop style demonstrations. So,
Make this go away. No, top away. Sweet. And then this little guy too. That thing. Let's get it out of the way. Usually it can go away.
Maybe if you click on the slider, it'll
Tries clicking on it.
Nope. No, that didn't work. There's a minimize of some sort.
Sorry.
I'd voted meeting drops. Right there.
Ta-da.
Perfect.
Thank you. So I'm really glad to be in the Punch for All session. It's just a great title, and I'm excited to see all the work that the outreach team is doing, and I hope that the SOC and the Science Operations Center can meet that and aspire to do as much public and open science as we can. So the SOC is a rather large group of people. So we have Derek Lamb, Dan Seaton, Ritesh Patel, myself, Sam Van Kooten, Chris Lauder, Sarah Kovac, and Matt West. We're not all here in person, but they've all contributed great things to the SOC and are always happy to talk about the work that we're doing and try to engage with you about things that we can do better or new ideas you have. So please reach out if you see us or just keep in touch. That's the main theme of this talk. So what is the SOC doing? We have many observations that we're combining into one virtual observatory. As you've heard so far, we observe at a 4-minute cadence. And so we have the nifty inner field of view showing here on this animation on the right. And then we have the 3 WIFIs rotating around. And so this is a bit of synthetic observations that we've put together using gamma simulation. So you can see a CME that just moved out up into the top left of the field of view. And it will repeat if I click on it. There we go. So it hopefully looks simple and elegant, but there's a lot of steps that go into making this kind of product. So this is an example of one of the total brightness images that you might see or that you will see after launch. But the steps that go into making this are rather involved. We start in the top left of this visualization with a level 0 image. And there's actually a little bit before that where we just get the data from the satellite and we try to make images from the raw packets. But once we have this level 0 image, this is the first thing that'll be available to the science community. It'll be a FITS file with all the information that came at that time of observation. And so then the SOC takes that level 0 frame and does a lot of calibration. So we go through level 0 to level 1. That's the top row of this figure. It's got a lot of tiny text that I'm not going to go through in great detail. We'll highlight some of the features. But just, we're doing the photometric calibration here. And then, is there something? Okay. And then we move from level 1 to level 2. So you see that in the middle, the left middle section, where we take these individual frames and we make the first mosaics. So the trefoil, that little pattern of the 4 images combined. And then the last step of processing, we do the F-corona subtraction and the star field subtraction to make the level 3 images on the far right in the middle. In addition to that, there are a few more steps. The wind speed plots we'll make available. We make low noise products where we take these every 4-minute observations and we combine them into a 32-minute observation with low noise properties. So that was a run through of the data products. We're going to actually spend quite a bit of time in this next talk after me to talk about what the data products are. But I just wanted to point you to a list of where we've made available all the products and all the product codes. So we'll go together in a little bit in an interactive way. But each product is defined by a level, like we just talked about, and then a product code. So you see here level 0, L0, PM1. So that's a level 0 image that's polarized in the -60 direction, and it's a Wi-Fi 1 image. So all those components of the code are very descriptive. We don't expect you to memorize them or know them all. That's why we've made it available in our documentation that we'll go through together in a little bit. So every product is described. And if there's anything unclear, as always, we're happy to get feedback of how to make these kind of descriptions more clear in the documentation. So the levels that we've just looked at, we had level 0, that's almost straight from the satellite, no calibrations applied. Level 1 is the photometrically calibrated, so you have the nonlinearity corrected, you have the point spread function correction, and a lot more other features. The level 2, we have trefoils with the polarization resolved. The level 3, we've done really highly calibrated processes to it. And that's the data that we hope is most useful for your science. We've removed the star coronas and the stars in the F corona and tried to make it the most readily useful. It's still beeped. It's fine. And then finally, there's a level Q product that I realize we haven't talked about much, but there may be interest in the community, I realized from yesterday's discussions. So these level Q are quick punch products. They're a lot like the level 2 images. They don't have the F corona removed. They don't have the stars removed. We provide an F corona model with them, but it's not as high quality as the level 3 F corona model. But the important detail about them is that they're much faster. So the level 3 products, because we do all this calibration, they come at a delay, like they're weeks after the observation. And so if you're trying to do space weather forecasting, that's not going to do much good. And so the level Q products come about immediately and will be available through the standard methods of access. So let's hit a few highlights of what actually happens in the pipeline. We're just going to look at a few details. So this is the level 0 to level 1 point spread function regularization. It's one of my favorite steps because it was so exciting to see it actually start working. And the image on the left, you see examples of stars in the different parts of the image. So in the top left, you see there's this tail that extends down and toward this middle. Whereas in the bottom right, the tail is extending to the middle the other direction. So that's the coma effect. But then through some mathematics that's described in the paper Coma Offit that Craig alluded to earlier, we correct the coma, and you see the stars, the examples on the right now, where they're nice and circular and don't have this artifact of the coma. To convince you even more and make it more obvious, this is a synthetic image of just the star field. If you can identify where in the sky that is, I'd be impressed. Because it's real data in the sense that the constellations are correct, but it's synthetic that we haven't observed with PUNCH, obviously. And so you see a coma effect in the left, and then we've corrected it in the right frame. And that's going to occur in all the WIFI images and the NIFI as well, to make it so that we can mosaic them together seamlessly. So when we move on to level 1 and level 2, that's just one step of the level 0 to level 1 processing. There are quite a few more, but we don't have time to go into all of them. With the level 1 to level 2, we start with the polarization resolution. So the polarizers are rotating with the spacecraft. And it makes it much more complicated to figure out which frame of reference you're in. The polarizers are also not perfect. There's a slight offset, maybe, in where they're aligned to. There are other effects. So Ritesh Patel has a poster out in the hallway about the IMAX effect, where because of the huge field of view, the WIFI images have a polarization artifact that can occur, and we have to correct that as well. So we have this package called SopolPy, which allows you to load your data set, specifically PUNCH in this case, but we have it designed so it can apply to other data. And it converts it from maybe this arbitrary satellite frame into a standard frame, or to the beat brightness and total brightness frame, or the Stokes parameters, however you want, what system you want. It'll help do the conversion. This was an exciting result when we saw this. It's not always this perfect so far in our calibrations, but to convince you how good the PUNCH data could be, this is 2 WIFI frames that have been overlaid with you see the CME effect moving out here. But you have in the top right, you have a WIFI, and the bottom, you have a WIFI. And if we do all of our calibration perfectly, which I understand we probably don't do it perfectly, but if we do it well, the seam of the mosaic goes away. So you'll see one virtual instrument. And that's really what we're working toward, and what our main goal is, to make a seamless product that will enable the most science possible. We talked some about the F corona yesterday in our pre-meeting. And it's a large part of open development that we could continue improving even after launch. So right now, we have an implemented system where we take a bunch of observations. So we can use a couple months of observations. Every 6 hours, we'll accumulate those observations and build an F corona model to subtract from the images. So just to give you an idea of how this works, on the left, you see those two curves, the blue and the red one. The time is on the x-axis. So we have a bunch of observations for each pixel, each image. So here there may be 1,000 images that we're using at the same time to build an F corona model. And the brightness is the vertical axis. And so you can imagine there's a lot of K corona fluctuations and a lot of other effects. But we want to fit the F corona model to it. So that's the red curve here. So we've used quadratic programming to fit a curve to the bottom. And then we can sample and measure this curve at a specific point in time. And that's the brightness according to our F corona model. So it encompasses a large amount of data in a short snapshot of an F corona model. And so we can build these every 6 hours and keep a continuous model that we can interpolate and very precisely remove the F corona. I did say that there's open research that could be done here. There's lots of ideas of what to do to build an F corona model. And we want your feedback of, does this F corona model after launch work well enough for you? And if not, what would you do differently? We might not be able to implement it immediately, but we want to be able to communicate about ways to make the data better. Another really cool thing that we do is the star field subtraction. So you'll hear a talk in a little bit from Sam Ben-Kuten. But on the left, you have a level 2 type image. There's actually been some processing applied to it. And you see the stars very clearly. And so we take a bunch of observations. Once again, like we can take months of observations, and we build a model of where the stars look like. And so this is a synthetic data product we've made where we've modeled the stars. And then we subtract that off, and you get this starless image on the right. This is, once again, synthetic data. So we'll have to be very careful after launch to make sure that we can match this quality. But we're confident that the algorithm, the idea that we're using, is very effective. So what you've all been waiting for, maybe. How do you get the data after launch? So the data will be available, as Craig mentioned earlier, to the Solar Data Analysis Center. So your standard methods of using the VSO through a web query, but we're planning to have support so that SunPy can have a FIDO query. And so you can request data in that same method. And so on the right, we've been working with the VSO to get everything set up properly. So you see a screenshot, actually 2 screenshots stitched together. But you can see, if you can read this all the way in the back, which I doubt you can, the punch data is included here. So it'll be available as soon as the commissioning period is finished. The level 0 products are planned to be released. Now you have to wait a little bit longer, but I can tell you that you'll wait a little bit longer for the level 3 data. Luckily, I'm pretty much done with my slides, but I'll just fill time while you fix it, maybe, or
Actually, yeah, because we have to wait 30 seconds. Don't touch anything. Oh, yeah, yeah. Let's take some Q&A.
Q&A, yeah. So before I say Q&A, we have a GitHub where you can interact. I was going to show where the discussions button was. We'll do that once we get the screen back on. But for now, do you have questions for the SOC as we reboot?
Yeah.
Hi, Arno, thank you. For the PSF deconversion, does it work for the NFI when you are inside the limited zone, which has highly distorted PSF due to the nature of the instrument?
Yes, it has a PSF model for each region. So if we make our model fine-grained enough, it should apply to that region and be able to capture the effects, and even in the highly distorted vignetted region.
Okay, yeah, I'm curious to see that.
Yeah, it'll be exciting to see real data.
Yeah, exactly.
Any more questions while the screen wakes up? Phone?
Thanks to you and the team. Fantastic job you're doing. You showed a brightness picture of the F corona. I assume you're also going to do the polarized brightness of the F corona?
Yes, we build a model of the F corona for every satellite, like every product that we're making. So we have the polarized F corona and the total brightness. Yes. Oh, it's back. Great. There's a QR code if you want to scan and go to the GitHub, or the address is the top. I think, let me just see. Yes, that's pretty much all I wanted to say. And then we're going to have Chris come join. And he's going to go through interactively. He's going to first introduce some more about the data products. And then we're going to hopefully have people open the GitHub and open an example notebook, so that way you can manipulate some of our synthetic data right now.
Chris, come on over. A guided tour for the punch data. This is Chris Lauder from Southwest.
Yes. Okay.
What was our trick for getting rid of this thing down here?
Oh.
Hey, Cameron, what was the trick to get rid of this thing down here?
So like more and then like, oh, I shaded it. I got it. Where's the reps? Oh, I think it's a keynote. It's fine. Okay, it'll be fine. There's lots more that can go wrong in this talk, so we'll see how it goes.
So get this down.
Yeah. Okay. So I'm going to talk about punch data. Thank you, Marcus, for giving a great tour of all the SOC activities leading up to how to get the punch data and how to work with it. So this is a work a lot of us here in the SOC. Oops. Okay, so you guys have seen this diagram a bunch. What data products are we making? There are lots of data products that lead all the way up to these final data products. These are probably going to be the data in science products that most people are going to care about to do scientific analysis with. Our level 3 data products, ones that have been through the full pipeline, fully processed. We'll go through these. Marcus mentioned some of our 3-letter identifier codes for some of these. So these are the codes that you guys will probably become most familiar with in interpreting data products. VAM, PTM, PNN, PAM, and PAN. They just roll right off the tongue. VAM, VAM data products are extracted solar wind speed products. These are Raphael-Atti's code doing flow tracking to extract, in addition to these beautiful plots of the actual wind speed overlaid on top of NIFI data, we'll also actually have WCS compliant, the extracted wind speed data products as a 1440 or so azimuthal bends around. We also have the 4K by 4K images as well. We also have our PTM data products. These are the polarized trefoil mosaics. There is a scheme behind these codes. These are brightness and polarized brightness, and also clear mosaics. These come every 4 to 8 minutes and are 4K by 4K. They do, however, have the gaps in the trefoil. We also have our PNN products, which are brightness and polarized brightness, full resolution images for NIFI. These are just the NIFI field of view. They're 2K by 2K though, and they also come every 4 to 8 minutes for the polarized versus clear. We also have our PAM data products. These are brightness and polarized brightness. These are summed every 32 minutes. So over one rotation set of spacecraft, in 32 minutes, you'll get a 4K by 4K image, which are low noise data products. So we try to take advantage of the overlap between these different fields of view to beat down the noise a little bit. And then we have a corresponding PAN data product, polarized, brightness and polarized brightness. These come every 24 minutes and are 2K by 2K for just the NIFI field of view. But again, these are the same kinds of low noise data products. So these are sort of the set that we think most people will end up using. And we'll come back and talk about these data products more in a bit. So you get a FITS file. What's inside the box here? We built the pipeline to use IndyCube sort of as the bit that's passing things around the pipeline. This really bundles the data with a couple of other things. First of all, every pixel in our data has a corresponding uncertainty corresponding to that observed pixel. So you'll be able to use that to give error bars and things. We also have a WCS, World Coordinate System, that again, for every pixel describes where that pixel is in the field of view and in space. So you can use that to do data transformations. And we'll talk more about that later. I'll actually show you guys how to do that. We also have metadata associated with that. So we have transparent and self-describing metadata. It's fully FITS 4.0 compliant. And we really tried to make this metadata not just human readable, but human enjoyably readable. So hopefully when you open these FITS files and you open the header, it'll be a joy to just read through. I get joy out of beautifully written FITS headers. We're also taking advantage of FITS multidimensional nature, so we can store three-dimensional data inside these. This will be the bit that maybe is a little tricky to deal with, but when you open, say, a bit of polarized data, a PAM data file, it's going to be three-dimensional. It will be 2 by 4K by 4K. The two layers in this are the brightness and the polarized brightness, and you'll all see in a minute how to actually go about using that. So what's their name? When you find this PUNCH data product, it's going to be this long string. We've tried to organize this well so you can see immediately what every data product is. The mission is PUNCH. The data level, level 3, Marcus did a great description of all the various data levels. Here we're doing an example product code of PAM, and then we have our timestamp organized with the year, month, day, hour, minute, and second. And then finally, we've reserved a section for reprocessing. So if we do go back and reprocess data, you'll also have, in addition to the information in the metadata that describes all the provenance of how the file got to creation, we'll also have a file level version of that as well. So once you open one of these, what's actually inside of a FITS file? We're rice compressing the data. These data are big, and so rice compression can help make the file size a little bit smaller. Because of that, when you open one of these, the primary HDU, if you just open it natively, will be empty. This just contains information about the compression scheme, about the rice compression, so you can move beyond that. The first HDU, however, is going to have that primary data and that primary header. And then we've also stored the uncertainty and the uncertainty header in the second HDU. You have to think starting at 0 for this. So the 0th, the first, and the second. These data are readable with the standard AstroPy FITS framework. So I'll show you an example of that. And you can also read it into an IndyCube object pretty easily. And you can also read it into a SunPy map, which we'll show a little bit later. And that incorporates some of the WCS information as well. We have code inside Punch Bowl, which I'll show you guys in a bit, that can read these things into IndyCubes. And we also have some IDL scripts that are at the URL below. I'll show this in real time, where we have IDL tools that you can read in our Punch data. So let's talk about one thing. The Punch field of view is big. You just won't believe how vastly, hugely, mind-bogglingly big it is. So here's an image of the sun from AIA. There's some stuff around this. We'll get to that in a second. Just for context, as we zoom out, this is our full field of view for the Punch trefoil mosaics. It's big. It's really big. Craig has always said that to really fully appreciate this, you have to be in a planetarium dome. We should get that data out there. It's great. Okay. So because of that, we need to take a brief aside and talk about coordinate frames for a second, because that big field of view means we have to think a little bit differently about how we treat coordinates. So here I've drawn just a little cartoon, not to scale, obviously, diagram. Here we have the Earth, the sun, a satellite around the Earth, for instance. Let's say we're imaging close in to the sun. We might be able to get away with just using a flat sort of field of view type of projection, a tangent plane kind of projection. However, let's say that you have the Earth and you decide to launch 4 satellites around it, and they're imaging much wider field of view as sort of a combined mosaic field of view. Can we assume that same sort of tangential plane? Can we just scale it up to be big enough for the Punch field of view? No, that's not going to quite work. We have to start thinking about sort of curved coordinate frames going across that field of view. We have to start thinking beyond the flat 2 dimensions and start thinking about other coordinate frames. So We have different coordinate frames. Again, all these are described inside the WCS when you open these. For the NIFI field of view, it is compact enough around the sun nicely that we can just use just a tan projection for this, just a mnemonic projection. For the WIFI fields of view, these are a bit wider. So we're using an azimuthal perspective, an AZP projection. If you're loading these in with SunPy and AstroPy, it will do a lot of the work for you behind the scenes. So you don't have to sort of sweat all the details, but this is useful to know. These are for level 0 and level 1 data products. When we start moving to level 2 and level 3, the NIFI focused field of view data are still on that same mnemonic tan projection with some distortion in this. And then also at level 3, our mosaic data products are now an azimuthal equidistant projection, or ARC, ARC projection. I feel like my entire talk is just 3-letter acronyms at this point. Sorry about that. Okay, we also have, as Marcus mentioned, quick punch data products, which have very low latency and are also going to be freely available through the same sort of portal. For our quick punch mosaics, these are still the same projection, azimuthal equidistant ARC projection. You'll just notice that it's been cropped down a little bit closer in to try to avoid gaps in the trefoil while still keeping that low latency. For the NIFI quick punch products, these are also, again, the same mnemonic tan projection. Okay, so how do I plot punch data? This is where we're going to do sort of a flipped classroom thing. So there's going to be a pop quiz. We're going to do a live code-based demo and a live notebook demo. So while I have this QR code up, you guys should scan this and go to the Punch Mission GitHub page.
Hey, this is going to get complicated somewhat.
Yes.
So if you run into problems, I think the SOC members, I'm volunteering them, I'm happy to come and try to help you if you just raise your hand. And if there's like a common problem, we'll try to address it in the entire.
I should also say that we're going to be, I think most of us are around for the next 2 days. So come find us and ask questions because we are here to help. Okay. Oh, yes. Sorry. There's that QR code. Also, if you just search GitHub Punch Mission, you'll be able to find us. Although we found out this morning some other Punch Bowl code has overtaken our search engine optimization, so we need to. Okay, so let's pull up the GitHub. And I'm going to do one thing to load this in the background, so ignore the screen for a second. As much as you're tempted to look, don't look. Okay, so if you go to that QR code, blow this up just a little bit. Also, a live demo has never gone wrong. Okay. So if you go to that URL, you'll end up at the Punch Mission GitHub page. This is sort of our main portal where we'll be having all of our code repositories, as well as a discussion tab that I'll show you in a bit. We have a nice animation here at the top. There is a description of what Punch is. There's a great code link here about how to get started with Punch software. We've actually linked to things like contributed tools. So we have examples of, I think we actually just uploaded some of these this morning. So it gives a sort of a description of this tool set, the language it's in, and then a link to any documentation, paper, GitHub, etc. So that's linked from the main page. We also have a link to synthetic data that you can download. So once you get your hands on the notebook that I'll show off, if you would like to get access to more synthetic data to run through your own example notebooks, you can click on here. The format of this is still subject to change a little bit. Some of the metadata might be a little bit differently, so avoid hard coding anything. But you can get access to a lot of the level 3 data products from that link from the Punch Mission page as well. If also on the same page, you'll notice that we have our other repositories, some pinned repositories. So we've spun off some of the main bits of Punch. Punch Bowl is the main scientific processing pipeline code that does all of our analysis or reducing down to level 3 data products. We also have other packages, things like regularized PSF is a separate package, SupPy is a separate package. And again, you can find all of these here on that GitHub page. There's also a discussion tab at the top where if say, oh, look at this. Here's a thing about upcoming science meeting. Aha. So come here, you can add into a discussion. Say if you find an issue with the code, you can open an issue directly, or if you just have a question, you can ask a question here in the discussion tab. Feel free to join the Punch community here on our GitHub page. Okay, so let's go to our science processing code, Punchbowl. So again, Craig has been great in like leading the way with this open science development of our processing code. So we have put all of our code here out in the open so you can take a look at it. You can fork it from, well, I'm not logged into GitHub, but if I was, you could click on fork here and create your own version of it, suggest improvements, push it back in. We have all of our code here as well as instructions on how to install Punchbowl. But the thing that I really wanted to show off was up here. If you go to our GitHub page, in the upper right corner are our documentation files. And here we give sort of a whole set of dynamic documentation that will continue to evolve as our code evolves. You have things like describing what is Punch. We shouldn't have to explain that here. But we can talk about how to access Punch data. It gives an overview of everything that I talked about today. So if you don't have my slides, you can come back and just take a look at this. A whole section on data projections, our data structure. As Marcus showed earlier, here is a link to our data products. So we showed a couple of these, but there are a lot of data products. And this gives a sort of cheat sheet for all of the various three-letter codes that we have, just in case you encounter a Punch data file and are curious what it is or what you want to use. We also have for our metadata a whole description about what every keyword is and what the actual comment is, what this keyword actually means. So if you're ever lost, you can go take a look at this documentation and or just come ask us questions because we're happy to answer. Okay, let's go back to our documentation. We have a lot about the data. We also have the pipeline documentation broken down. So we have every module in the pipeline has a corresponding documentation page. So what's your favorite module, Marcus?
That's just saying we should look at the PSF correction.
Let's look at the PSF correction. Excellent choice. Okay. So in here, we have a description of the actual module, the concept with links to any documentation. Here it's pointing to the package itself. We have an example of how to apply the correction. The way we built a lot of these modules is that they can be called outside of the main data science pipeline itself. So you could call some of these individual functions manually in your code if you wanted to. You could import them just directly from Punchbowl. It's also, like I said, dynamic. So if we make any changes to the code, any documentation here will change automatically because these pull all directly from our actual modules and are built on the fly. Now, this is the part where it gets interesting. If you click down here or up at the top, we have a set of example Jupyter notebooks where we highlight how to use the data. The guide to data in particular is a good one. And now this is the moment of truth. Cross your fingers. If you scroll down to the bottom of this documentation, you can launch an interactive version of this notebook and run it in the cloud in real time. So let's see if this launched. I'm going to refresh the page. Yes.
It's been going up and down.
Yes. Yeah. They've been having network connectivity issues. See what I said about a live demo never going wrong?
So there are only 2 notebooks shown there right now. We're
Yes.
planning to put more, but also if you have ideas or you make your own notebook and you want to contribute it, in addition to the contributed tools where we'll just link to any code that you've done that is related to Punch, we're happy to incorporate Jupyter notebooks that you prepared that explain how to do something very specific with the Punch data. If you want to overlay it on some other data set, if you make a notebook that shows how to do it,
yeah,
we're going to try to incorporate it.
Okay, is this visible from everybody in the back? Okay, so if feel free to launch this and follow along in real time as we go through this. So there's a lot of other writing here that talks really about how to get things installed, but we should be able to just import all of our libraries that we need. Again, a lot of this is very standard things: AstroPy, Matplotlib, IndyCube, SunPy. You'll also notice that we have built in some sample data directly into this. So you can import directly from punchbowl.data.sample an example PunchPam data file that you can use to work with. So we've loaded the data. We can then use AstroPy fits to just open it like this. So we're saying with fits.open, that PunchPam example file, reading that into an HDU list. We can then get out, again, this comes back to, remember, our first HDU is the one that actually stores the data. So if we take that HDU list, the first element of it, not the 0th, we can then get the data out, put that into a data object, read the header out, put that into a header object, and then we can read the second HDU data and put that into an uncertainty variable. And so now we have our data, our data, our header, and our uncertainty. So I'll actually run that. If we take a look at these, we see and do the shape of each of these. The data is a 2 by 4K by 4K, and the uncertainty is a corresponding 2 by 4K by 4K. If I print the header, it's not going to be pretty, but we can do it. Yes, the joys of fits sometimes. Yes, you can actually read this out as a header. Yes.
If you want to make it pretty, crop the print.
Ah, yes.
Activity. So if you remember that headers are objects.
Yes, there we go. You can also call particular cards. So I could say, what is in axis 3 of the header? And it will give me my value back.
Thank you for this great description. What is exactly the uncertainty and how we calculate that? Based on what it is calculated?
Yes.
I'm very interested to know.
Yeah, so Marcus might have more, but we basically carry it along for the ride through the whole data processing pipeline. And so as we apply each module, the effects of that are calculated and carried through. But Marcus, you might have more to say.
Yeah, so it's one of the really challenging, complicated parts of the pipeline. So you start with an observation, and you can kind of estimate the uncertainty in the observation with the shot noise and the read noise and all of those components. But each step of combination, each processing step, modifies the uncertainty. So I think we could probably do a better job of describing how the uncertainty is modified in each step, but it's in the code base, and we will put it better in the documentation. But for example, the step of making a mosaic, we've reprojected the images and we're combining them. Well, there's overlap in some parts of the image, so the uncertainty has to combine from one image to the other. So we combine it in quadrature and propagate it forward. And so that kind of operation happens in the pipeline in the background for each step of processing. And so you come to the level 3 product where we have an estimate of the uncertainty that we think there is in the data. Hopefully that proves to be useful with where you can trust the pixel or not. It'll be really useful for the obvious spots where the uncertainty is super high or extremely high, way above the pixel value. You don't want to trust the value of the pixel. But if the uncertainty is reasonable, then you can rely on the pixel value for actual science. So we're trying to push that a number is kind of useless without its uncertainty. So we're trying to get that thought process going with the punch data. It's not perfect because we don't have it fully documented in the here at the moment, but that's something we're working on.
Yeah, keeping track of that really enables us to do that merging and weight where we have overlap between instruments, weight those appropriately. Okay, so I realized I've had too much coffee and I'm moving too fast. So I'm gonna take a step back for a second. How do I get to the binder? I went fast, sorry about that. If you go to the Punchbowl repository, so let's go back just to Punchbowl. So if you found your way here, in the upper right is a read the docs link. So you can click on that. That will then take you to the documentation page. And then from here, if you click on examples up at the very top, you'll get to the 2 examples we have at the moment. if you click on guide to data, not the quick punch one, but the data guide one, click on that thumbnail and then scroll all the way down. It has a statically rendered version of it that you can browse to. But then if you scroll all the way down to the bottom, spoilers, it will give you a link to launch Binder, as well as download the IPython notebook or just the Python source file.
And if you don't like scrolling, at the very top, it gives you a reminder, go back to the top. Go to the end.
Oh,
download.
yes.
And so just click that button and it'll scroll for you.
Okay, shortcuts. Okay, so let's go back and close some tabs. Okay, so we have the header. If we scroll down, it's a long header. And yes. Yes, sorry. To run a command, a cell within here, hold down Shift and hit Enter, and that should run. If you hit Enter, it will just do a new line. You can also just hit Run All at the top, this little 2-arrow button, and that'll just run the whole notebook for you, and you can look at the results. So we can take that header, which contains all the information describing that observation, and we can pass it into WCS, which is, we've imported that from AstroPy. And if I click on that, if I hit Shift Enter to run that, you'll see that we have the WCS that describes this particular data cube that we have. There are 2 axes. There's a helioprojective longitude, a helioprojective latitude. You'll see these are in the ARC projection. And then there's a 3rd axis, which is this sort of Stokes axis that we've called it, which describes the layer that contains brightness and polarized brightness. We have all of our CR vals, our CR picks. We have our PC matrix. We have our C deltas, and then the n-axes. So this describes that full 3D data cube. This is then a WCS object that you can pass into various AstroPy functions to do things like reprojections or get coordinates for particular pixels. We also have, in addition to helioprojective coordinates, we've defined a secondary WCS that is in celestial coordinates. That's not relevant when you mentioned this the other day. If you then pass the header into this WCS object and tell it to use the key A, which is the secondary WCS, we have our RA and DEC coordinates. And it's again the same WCS describing the same sets of pixels, just in RA DEC coordinates. So that way you don't have to do math. Okay. Now, how do you plot this data? We can also load it into a SunPy map object. If we take our punch PAM data product, pass it into the SunPy map function that we've imported, we can create a data map. We can take the 0th layer of that to just get the total brightness out, and then we can just say dot plot. It's going to warn us about this for right now. We're working with SunPy to deal with the fact that we have this 3-dimensional data. So eventually you won't see this error message. But there you go. Beautiful image, right? It's not just the projector. The dynamic range of this image is huge. So we've had to work on other ways to project this. We can also read out, we'll come back to this in a second. We can also read out the other layer in the data, the polarized brightness, by just taking the first element out of that. And that gives us the polarized brightness. Again, we can't see much with that. So how can we plot this in a better way? We can take that same map object, and we can set sort of a log scale on that data, just using the SunPy map objects plot command. If I run that, there we go. That brings out a bit more detail, which is nice. Oh, wait, I need to change this notebook on the fly. Nothing bad is going to happen here. I'm going to go up to the top all of a sudden, and I'm going to change my imports. I'm going to say now, I just remembered we made a fancy punch color map that we could use, almost like we perfectly planned this. I'm going to say from punchpole.data.visualize import CMap punch, and just re-import our libraries. Let's scroll back down to where we plotted these. And I am now just going to say, oh no, remember about live demos going wrong? I can no longer click on this cell. Maybe I can go down like this. There we go. Okay, let's set our CMap to be the punch color map. There we go. So now we've defined it in this. Thank you, Craig, for your help with defining, with your beautiful knowledge of color spaces, in being able to define this color map for the punch data. Okay, and again, you can import this directly from Punch Bowl. We'll also work with SunPy to get this incorporated into their code so that it can run when you plot a punch map natively. Okay, we can also do things the old-fashioned way by using matplotlib. So here's a much more complicated way of plotting this. I'm not going to go through all of this in detail, but basically you're setting up a matplotlib plot. We are showing an image, which is the actual data, and then we're setting up coordinates on top of that using our WCS data to apply some grids. We can plot that. There we go. Oh, I changed my mind. I'm going to set the color map to be the punch color map. And there we go. And it's too big for the screen. I told you punch data is big, right? Okay, but there you go. Then you get a plot with color bars, you have axes, grid lines, et cetera, et cetera. Okay. We can then also do the same plot, but use these celestial coordinates instead. So now we're just using that secondary WCS that we defined, and we're setting RA and DEC coordinates. And this should run. And there we go. And you'll see these are offset, right? Like our mosaic images are defined to be nicely aligned in this helioprojective coordinate system. Celestial coordinates will vary from that, right? Because our solar system is not exactly perfect. And so it's not a criticism of the solar system. And so here are our celestial coordinates. And you can see we have RA and DEC axes on this as well. Okay. Now we can also use our WCS to reproject the data. So here what I'm doing is I am taking, blow this up a little bit more, taking our data map, taking the WCS object from that. I'm doing a deep copy so that I'm making a totally separate version of it that doesn't interfere with itself. And then I'm going to change some parameters. I'm going to keep it to be helioprojective. I'm going to keep degrees. I'm going to make the new shape 1024 by 1024. I'm going to set the CR pix to the center of that, 512 by 512. I'm going to change the CR val to some distant value. It's a bit different. Change C delta is going to be the same. And then I'm going to distort the PC matrix so that it's not quite so aligned. Then I'm going to basically use SunPy maps, beautifully built-in reproject functions, to take our SunPy map data map, just say .reproject2, and then give it that new WCS, and pass that out into a new map object, plot it, and then show it. There we go. So it looks horrible, right? But I just chose some arbitrary WCS for this. The sun is somewhere off in the corner of that, but you could reproject that to whatever other WCS, whatever other field of view you might have. Okay, we're almost to the end of this, and then we'll break out into something a bit more interactive. Yes.
Are there any questions?
Yes, very good point.
Use these tools to plot high altitude aurora.
That's one of those good opportunities where if you figure out how to do it, you can contribute a notebook.
Yes.
Because we don't know how to do that yet. We haven't tried it, but. Yep.
Group of people who are interested in helping out on this processing, or what can they have? Do you have synthetic data for high altitude aurora, or those are without?
So we didn't really simulate the aurora in our synthetic data. We'll obviously have the effects in the real data. So we don't have synthetic at the moment, but if you wait a few months, you'll have real data.
Very nice overview. So just a small comment. When you take log to enhance the brightness, you see that it artificially fills the occulted part.
Yes, yes.
Yeah.
We have like uncertainty masking in the data too that we talked about earlier. So like that occulter part is masked out as infinite uncertainty essentially, right? But yeah, that's a good point. When you plot it that way, what he's talking about is going back up here, you see the occulter in the center, right, in NIFI. But when we did the log plotting, it artificially removed it from that. Yeah. Thank you for pointing that out.
Yeah, just a quick remark. I saw that for NFI, you're using the tan projection, but I think we can provide you more details on the distortion aspect. So that should put you closer to finding the stars in the field of view.
Okay, perfect. Yeah, I think at like level 0 and 1, we still have a distortion lookup table bundled with this. And then at some point, we project it to sort of the idealized frame moving forward. But yeah, that's good. I've unplugged the key. Yes.
But you mentioned that the images are over the curved plane, and is there any of these projections that is useful for synergistic application with in situ spacecraft that you can plot like in situ spacecraft and see where there is the intersection of the curved?
So we've got, yes.
You know what Sam Badman did for us?
Yes, and we're working with Sam Badman on getting some of his example notebooks into the
Sorry, yeah, he has a poster that shows something about, I didn't look at it closely yet, but shows kind of the same thing, so we should all connect about making this happen.
Okay, cool, thank you. Let's move down. So we projected the data. We can also use IndyCube, right? We've used reading it into just data arrays and AstroPy WCS objects and AstroPy header objects. We can also read everything into an IndyCube object, which is this amazing thing that bundles the data, the WCS, the header, and the uncertainty all into one compact object. That then is great for passing through something like a data processing pipeline for a spacecraft. So we can run it like this. And there we go. Now it's a 2x4K by 4K. The axes are described within here, the data type, etc. So we can also do the same kind of reprojection. This is, again, just the same setting up of a new arbitrary WCS and then reprojecting to that. Oh, but it's using my most hated color map. So why don't we change that? And there we go. And it's, again, just reprojecting to some arbitrary new WCS. You'll also notice, depending on your notebook settings, you can have an interactive sort of map plotting where you can toggle between the two states, brightness and polarized brightness on the fly. Okay, let's plot that. Okay, that's just plotting with some log scaling. We talked about uncertainty in the data as well. You can read these out and talk about the idea that we have an absolute uncertainty. We're compressing the uncertainty a little bit into an 8-bit number when we store it for the sake of data volume. Down here, we can plot the uncertainty as well. This is a long chunk of code, but we're basically doing the same thing that we did before, setting up axes, but now plotting the uncertainty instead. I think this is, there we go. So now we have the data and the uncertainty side by side. And so we're going to see that a lot of the uncertainty is driven sort of closer into the sun, where that kind of shot noise dominates. So I'm going to now do something totally live, just for fun. We'll see what happens. I'm going to do an example case. We have our brightness and our polarized brightness, right? We'll take a look at data and data.shape. It's, again, our 2x4K by 4K. So our first layer is our total brightness. This. And if I do .shape 4K by 4K. What if I took that brightness and I subtracted off polarized brightness? And then what if I took that and divided it by the sum of those things? I got something like a polarization ratio out of that. Oh, this is what I get for trying to do something in it. There we go. Yeah. We're going to complain about math that doesn't exist. But then what if I plot that image? There we go. You get something like that out of the data. So you can do all kinds of fancy stuff with this. That was the end of this sort of live notebook. We're going to open it up now. You guys can play around with this notebook in real time, create your own notebook. How are we doing on time? Or are we out of time? 2 minutes. Okay.
Well, no, this is moved into discussion.
Yes.
Yeah, so just we have 8 minutes till lunch.
Okay, why don't we move into like discussion, the questions and stuff.
And we're hoping we can find time. have kind of trainings online of some sort. So if you have questions,
Oh, yes, yeah.
we can go through these kind of things and more things later. We haven't worked out the details of that yet.
So yeah, the last slide I wanted to show off real quick is where to go from here. We have our GitHub discussion forum. Send us your analysis Jupyter notebook. So take this, do interesting things with it, and then please share them. Again, get your hands on this data and the notebook, and please break things, find places where things don't work, and break things in fun ways, do things that haven't been done before, and then use and remix all this too. So again, there's the QR code. Thank you.
So we can have questions for either one, Chris or Marcus.
Oh, I'll also say, come find any of us during the next 2 days, ask us questions. We might have a table in the back reserved too for office hours kind of thing. So come find us and yes. Yeah.
Any questions?
Just a quick comment as you guys are setting up your labs. I think you'll notice that there are a lot of really powerful, really amazing things in this Python environment. So if you're an IDL user, maybe this will be the kick you need.
Oh, okay. Yeah.
Chris, first, congratulations for taking this huge risk of a live remote. I know that it can be very stressful, and you made that flawlessly, honestly. Thank you very much. So, all right. So what I see here really shows me that this is we are already in the future, and thank you for that. So I now I have a question, and I am sure Craig's gonna again say that is again a question from Raphael the Crazy. My question is, be still in this future. What about, you mentioned this very large field of view that's great for dome projection, background projection. What about VR headsets? Have you had any thought on that? Because now, VR headset is becoming very popular.
Yeah.
Many people have that in the household, so it is both pertaining for scientific visualization, but also for the outreach people.
I was just thinking that, yeah.
Can you comment on the feasibility of having some materials that are VR compatible?
That's an awesome idea, but it's not an idea the SOC can probably pursue at the moment. Maybe the outreach team could think about, yes, maybe talk to him. And if you know a local solution, once again, if you make a little tutorial, we'll throw it up there on the GitHub. But for now, the SOC is not going to make VR products.
Okay, so I'm just dropping an idea for future you mentioned online teaching, online things.
Yeah.
I mean, I'm happy to help. I'm able to experimenting with an online attendance using VR headsets.
Yeah.
So I'll formulate that.
That's a great idea. Thank you.
Okay.
Fantastic presentation. That's really cool. So I'm a bit newer to the data pipeline, and I just want to make sure I understood what I saw. First of all, it's really, really valuable to have the photometrically calibrated total brightness, polarized brightness. And it's awesome that the uncertainties are also going to be in there. Will those uncertainties also include the F corona model as well, or do you have a way of propagating that into those?
I mean, they should be stored in the F-corona calibration data products that we generate, and then those could be applied.
Yes.
Yeah. Yes.
Okay.
Yeah.
And then my familiarity with other coronagraphs is that oftentimes the data product will have median subtraction weeks or a month or something like that, or mean subtractions. Is there anything like that in the level 3 data, or is this really just you've done the best gray light correction you can, the best starfield removal after run? Can I treat that as basically the polarized and total brightness?
Yes, that assuming we've done everything correct, that is our interpretation. So yes, and Craig wants to make a comment.
Sorry, I just have to jump in. Yes, it is the brightness, but it is the same kind of brightness you get from every other chronograph. Right. It's feature excess brightness with an unknown 0.1. Right.
Hi, I have a question about how the the full mosaic images are assembled, specifically, what's gonna happen to fast transient events when 30 minutes is a significant amount of movement?
Oh,
So we have the level 3 products that are every 4 minutes, and those don't include averaging. So it shouldn't have a blurring effect if that's what you're concerned about, I'm sure. So we'll have a regular product, level 3, that doesn't have averaging or low noise, and then there'll be also another product. So just make sure you're getting the PTM products that don't have the averaging.
So the full mosaics will be averaged. Will have blurring or fast changes.
the PAM ones. Yeah, the
Yeah.
full 32-minute low noise ones. Those should have.
Yeah,
that
so
would show.
there are 2 products. There's the PAM that he's mentioning, that is the average 32-minute version. And then there's the PTM, which is still a mosaic, but doesn't have that averaging included.
Okay.
Yeah. Good call on the figure.
So sorry about running out of time. I thought we are gonna have all kind of time to do like an interactive thing. We can push that until later. Time flies though when you are running Jupyter notebooks. So I apologize for that.
Okay, so any more final questions? Comments? In that case, I think we can go eat.
And Chris, just a question while I'm up here. The one that you're mentioning, that the PTM, it moves, right? It moves its field of view.
Yes,
So
that will rotate.
it rotates, yeah, which is kind of cool. All right, thank you. And I also want to comment that all of our talks are recorded and they will be up on our webpage. So if anybody like me wants to go back through that and hit stop every 10 seconds, and then, yeah, you will have that opportunity. It was really great. I'm so impressed with what you guys have done. So I have, well, first of all, we have lunch outside for the next hour. We're going to be starting up again right at 1 o'clock. Second of all, just a housekeeping thing. Please do, if you have trash or recycling, please do take care of that. We have trash cans right by the front door. If you can't find them, ask Carrie, Don, or me. And that's it. Go and enjoy your lunch. Thank you.